In the last chapter, we went over chemical equilibrium in a broad sense, encompassing a wide variety of reaction types in both the gas phase and in solution. Now, in chapter 16, we're going to look at a very specific and important type of equilibrium, that between acids and bases in aqueous solution. Let's just briefly recap the definition of acids and bases from the first semester of general chemistry. Under the Arrhenius definitions that you learned previously, an acid is a substance that dissociates in water to produce hydrogen cations, and a base is a substance that dissociates in water to produce hydroxide anions. To get a better idea of how acids and bases actually behave, especially in aqueous solutions, we need a related but distinct definition, the Bronsted-Lowry theory of acids and bases. Under these definitions, a Bronsted-Lowry acid is a substance that can transfer hydrogen ions to another substance, known as a Bronsted-Lowry base, which can accept hydrogen ions. Because most hydrogen atoms have only a proton in their nucleus, and a hydrogen cation has its one electron removed, Bronsted-Lowry acids and bases are also referred to as proton donors and proton acceptors, respectively. When a generic Bronsted-Lowry acid, HA, donates a proton to a generic Bronsted-Lowry base, B, the two new substances formed will be the protonated form of the base, BH+, and the deprotonated form of the acid, A-. These species will exist in equilibrium with the original acid and base. The protonated form of the base, BH+, is known as the conjugate acid of the Bronsted-Lowry base, and the deprotonated form of the acid, A-, is known as the conjugate base of the Bronsted-Lowry acid. A conjugate acid and conjugate base, then, are two chemical species whose formulas differ only by one hydrogen ion. Any set of two such species are said to form a conjugate acid-base pair. Let's use the notion of conjugate acid-base pairs to more closely analyze what happens in an aqueous solution of an acid or a base. Any Bronsted-Lowry acid in aqueous solution, generalized as HA, is a substance that can react with water in equilibrium to donate a proton to a water molecule, forming H3O+ hydronium ions and A- anions. In other words, water can act as a base or proton acceptor in equilibrium with an acid, forming the conjugate acid of water, which is hydronium ions. Base dissociation equilibria in aqueous solution follow the opposite pattern. Here, a Bronsted-Lowry base, we'll use ammonia for this example, is a substance that reacts with water, where water is now the proton donor, and the base is the proton acceptor. This results in the formation of water's conjugate base, the hydroxide ion, and the base's conjugate acid, which in the case of ammonia is the ammonium cation. In the context of aqueous solutions, H+ cations never exist in isolation. As shown a couple of slides ago, aqueous acids donate protons to water, forming hydronium ions. In reality, hydrogen cations can combine with more than one water molecule, depending on the particulars of the solution. However, we will consider all of these as hydronium ions for simplicity. And while it's possible to write an aqueous acid as dissociated into H+ ions in aqueous solution, if you ever see an equation written that way, just know that it's a stand-in for hydronium ions or other hydrogen water cations. We can treat H+ as equivalent to hydronium ions, in other words. Like with any equilibrium reaction, we can ask ourselves to what extent, say, an acid in aqueous solution will donate protons to water to form hydronium ions and the conjugate base of the acid. Whenever concentrations of these reactants and products are equal, the equilibrium will move in the direction that forms weaker acids and bases from stronger acids and bases, as determined by analyzing each conjugate acid-base pair. This means that for any aqueous acid, the extent of its dissociation into hydronium ions and the conjugate base of the acid is determined by whether the acid is a stronger acid than hydronium ions themselves, and to what extent this is the case. If the generic acid HA is an acid that is a stronger acid than hydronium ions, HA is said to be a strong acid since it will dissociate to essentially 100% extent. In other words, the position of the equilibrium involves essentially all of the HA converted into hydronium ions and A- ions in aqueous solution. If HA is a weaker acid than hydronium, the position of the equilibrium will be determined by just how much weaker HA is. If HA is somewhat weaker of an acid than a hydronium ion, then at equilibrium there will be mostly undissociated HA molecules with smaller amounts of dissociated hydronium and A- ions also present. And if HA is a weaker acid than water itself, there will be essentially 0% dissociation. In other words, at equilibrium, essentially all of the HA molecules remain undissociated, with only negligible amounts of hydronium and A- ions present. This effect is demonstrated on this set of charts. Looking at the column on the left, we have a number of acids ranked from strongest to weakest going from top to bottom. All acids that are stronger than hydronium ions, on this chart, perchloric, hydrochloric, sulfuric, and nitric acids, are strong acids that are essentially all 100% dissociated whenever they are in aqueous solution. At the other extreme, on the bottom of the chart, we have acids that are weaker proton donors than water itself. These include substances like ammonia, hydroxide ions, or elemental hydrogen. These are essentially incapable of donating protons in aqueous solution, and hence don't dissociate to any meaningful degree in water. Between these extremes, acids that are stronger proton donors than water, but weaker proton donors than hydronium, are normal weak acids. These exist in solution as a mixture of undissociated acid molecules, with typically smaller amounts of hydronium and conjugate base ions. In the column on the right of this chart, we have the conjugate bases of each acid from the left column. Notice, as indicated by the arrow, that the stronger an acid is, the weaker its conjugate base is. For instance, the conjugate bases of strong acids, such as perchlorate, chloride, bisulfate, and nitrate ions, are very weak bases that have negligible tendency to accept protons in aqueous solution. In other words, they are weaker bases or proton acceptors than water itself. At the bottom of this column, we have the conjugate bases of the very weak acids from the previous column, such as amide, oxide, or hydride ions. These bases are all stronger proton acceptors than hydroxide ions themselves, and so these substances cannot exist in unprotonated form in aqueous solution, only in protonated form as their conjugate acids. And finally, in between water and hydroxide ions in the column on the right, we have the conjugate bases of weak acids, which are themselves weak bases. Under equilibrium conditions in water, they will be partially protonated, coexisting as a mixture of unprotonated weak bases, protonated conjugate acids, water, and hydroxide ions. The stronger a weak acid, the weaker its conjugate base, and vice versa. There are certain trends that allow us to predict the relative strength of certain acids. The first group to consider are binary acids, or those that consist of only hydrogen combined with one other element. There are periodic trends that allow us to compare the relative strength of different binary acids. Firstly, if we consider the relative strength of acids based on elements in the same row of the periodic table, so here, for instance, we see the compounds formed between the second row elements carbon, nitrogen, oxygen, fluorine, with hydrogen, the trend is determined by the electronegativity of the element to which hydrogen is bonded. Hence, HF is the strongest of these acids on the basis that fluorine is more electronegative than carbon, nitrogen, or oxygen. Water is the second strongest, since oxygen is the second most electronegative of these four elements, and so on. Now, electronegativity only explains the trend when we compare between elements in the same row. For elements within the same column of the periodic table, bond strength becomes a more important factor. The weaker a covalent bond, the easier it is to split apart into two ions. Hence, if we look at the compounds formed between hydrogen and the halogens, we find that HF is a weaker acid than HCl, which is weaker still than HBr, and HI is the strongest of all. The fact that, as we move down a column of the periodic table, the elements become larger means that the bond they form with hydrogen will be longer. Longer bonds are, generally speaking, weaker, hence the observed trend. Notice that when comparing acid strength based on elements in the same column, the trend is opposite to the one based on electronegativity, which was the determining factor when comparing elements within the same row. So those are the two trends with regards to binary acids. We can also predict the relative strength of certain oxoacids, or acids that contain hydrogen, oxygen, and some third element. Typically, the undissociated form of these acids will have the hydrogen bonded to one of the oxygen atoms, which is itself bonded to an atom of the third element. For any set of oxoacids with equal numbers of oxygen atoms per molecule, the electronegativity of the atom bonded to oxygen determines the strength of the acid. The more electronegative this element, the stronger the acid. So for instance, HOCl is a stronger acid than HOBr, which is stronger still than HOI, as you would predict from the fact that chlorine is more electronegative than bromine, which is more electronegative still than iodine. For oxoacids that contain the same elements but with different numbers of oxygen atoms per molecule, the oxidation state of the central element correlates with the acid strength. The oxidation state also directly correlates to the number of oxygen atoms, with the next result being that more oxygen atoms per molecule correlates to stronger acids. We can see this trend with the 4 chlorine oxoacids. Hypochlorous acid is weaker than chlorous acid, which is weaker than chloric acid, and perchloric acid is the strongest such acid. Note that this tracks with increasing oxidation numbers for the chlorine atom, as well as the number of oxygens in each acid.